Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, RFEM. The topic for today's presentation is ADM 2020 Aluminum Design in RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Siska Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So regarding the content over the next hour today, we will begin in our standalone program, R section. So this is new with the new generation. And we're going to import in a DXF file to calculate the properties of a custom extruded section. Then we'll see how we can integrate this custom section into our FEA program, RFEM. So once we're in RFEM, we'll take a look at the structural modeling and loading workflow. We also want to define the member design input data. So this is going to be specific to the aluminum design, and specifically I'm talking about topics like effective lengths or unbraced lengths. We'll utilize design supports for deflection calculations. We will also utilize the aluminum design add-on. So this is an add-on that is integrated within the main program RFEM that allows us to perform the design according to the ADM 2020. RFEM will perform the analysis and the add-on will perform the design. And finally, at the end of the example, of course, we'll take a look at both the analysis and design results. So let us talk about a few new features that we have within RFEM 6 related to aluminum design when we compare this to what we previously offered in RFEM 5. So as mentioned, this add-on aluminum design is going to be better integrated in the main program. In RFEM 5, we previously had to open up a dialog box, define information like unbraced lengths. And in RFEM 6, we'll see that as we model the members, including the cross-section, the materials, we can also define immediately the effective lengths. The topic of effective lengths has been completely revamped within this new generation as well. So we'll see how we can define intermediate supports so that the effective lengths, or K times L, that's used for our unbraced lengths is calculated automatically. We also have added what we call design support. So if we take a look at our structure that we'll be modeling today, this carport, we have these small purlin members passing over the main cantilever beams. Well, this is a rather complex situation for checking serviceability or deflections because we have a small cantilever at the left end, the right end, but in between the main beams here, the element is supported at both ends. So we'll see how design supports can help us define more complex situations such as this. Now, the next two bullet points here I will not be showing in today's example, but I think it was worthwhile to point out that we now can consider transverse stiffeners according to section G2 when we are looking at the member shear design. I'll point that out in the example today. Also, single angle bending can now be considered according to the geometric axes if all conditions are fulfilled according to section F5.1. Previously in RFEM 5, we considered single angle bending according to the principal axes only. And finally, the detailed design output that we give for the member checks according to the ADM. We'll take a look at this at the end of the presentation. Previously in RFEM 5, we gave you variables, we gave code references, but now in RFEM 6, we're actually going to see the calculations laid out for us that we can follow line by line to determine exactly where the design ratio comes from. So we will begin in our standalone program, R section, and I'm going to import in a DXF file for my custom extruded section by going to File, Import, DXF. So we'll want to select the DXF file that's saved to our computer. The program will initially want to know what are the units that we have set within that DXF file. So we'll set this to inches. We're going to insert the DXF file at the origin 0, 0. We click OK through our dialog boxes, and we can see here that we have the line elements imported. Now we need to take a couple steps in order to actually calculate the cross-section properties of this custom extruded section. So for this, I want to right-click on the model name to take a look at the base data. And this will be the dialog box that pops up when we create a new model. Or in our case with the DXF file import, we can revisit it again. Notice the analysis method has two options, the finite element analysis and the thin-walled analysis. So we'll go back to the PowerPoint to explain the differences between these two, beginning with the thin-walled analysis. So this analysis type should be used for exactly that, thin-walled cross-section. So I'm talking about aluminum, steel, cold-formed steel, and so on. This is going to apply an analytical calculation. What we'll see is that the stress and force flow will be considered along the element length, but not the width. And what I mean by element is each one of these, such as the wall over here on the left, is considered an element. At the bottom, we have another element. So we'll see that stress and force flow along the length in the vertical direction, but not across the width from left to right with this type of calculation. Now, the torsional and warping properties are considered for those elements only. So you'll notice we have a few areas here in the upper corners that are not considered. Maybe we've modeled in fillets directly in our section. So these fillets will not be considered when we're calculating the torsional and warping properties. Now, the huge upside of the thin wall analysis is the ability to generate what we call subpanels. And these subpanels can be used to determine the width to thickness ratio of each of these elements. Once it's brought into RFEM, we can actually check local buckling. So this certainly sets us apart from a lot of other competitor programs, is that we do have the ability for these custom sections to also check for local buckling. Now, looking at the finite element analysis, the second option, this should be used for more massive type cross sections, concrete, timber, and other. Are situations too where maybe a custom extruded aluminum section can also be used for massive, and I'll show you a quick example of that today. The finite element method will be applied here as opposed to the analytical calculation. We will see stress and force flow along the element length, so in that vertical direction here, but also across the width. And with this method, the torsional and warping properties are considered for the full cross section. So fillets, you can see here these corners here that are kind of missing with thin-walled analysis will all be considered for those particular properties. Now, the finite element analysis is certainly going to be a quicker approach, which we'll see this with our example today. But the downside is that we do not get subpanel generation for those local buckling checks. So just something to keep in mind, some of those differences between these two options. So going back to our section, what we'll begin with first is the finite element analysis here in our dropdown. So we click OK. And what we want to create is a new part. So we go over to our navigator. We can simply right click on parts to create a new part defined by the boundary lines. The initial material needs to be set here. So we maybe have some default material, or we can create a new material. I'll go ahead and edit this default material by launching my material database. And over on the left, we have our filters where I can select aluminum from my dropdown, as well as the ADM 2020. And here, all of the aluminum materials directly from the standard, including the 6061 category, and we can see the individual materials listed out here. Now, for today's example, I'll choose the 6061 T6 for extrusions. I click OK. We see the material properties generated here. And up in the upper right, I want to use my arrow to highlight over all of the boundary lines. Now I'm going to hold down my shift key to deselect the elements in the interior here. So when I click OK, what we'll see is our part generated, But of course, we need to add in that opening in the center. So what we'll want to do then is to right click under openings, create a new opening. Same concept here where we'll choose our boundary lines. We can drag over those 4 center lines. I click OK, and now we can see our section is generated considering that opening. And really that's all that needs to be done for this finite element analysis. I can go to calculate all, the cross-section properties are immediately presented to me in table format here down at the bottom. So you'll notice that all of these properties can be saved with the model up here in the upper left-hand corner. This is what we would want to bring into RFEM, for example, for this custom extruded section according to the finite element. Now, we also have some graphical options over on the left. We can also view the unit stresses here based on applied 1 kip load or 1 kip foot moment. So that would, again, be all that's entailed for that finite element analysis. But we want to take this a step further to consider local buckling once we do get into RFEM. So what I will do now is to right-click to go back to the base data and instead change the analysis method to thin wall. I click OK. Now, everything that you have seen up until this point is still applicable for the thin wall analysis. We have to create the part, we have to create the opening, but we take it a step further by creating our elements. So I'm going to go to my navigator here and I'm going to turn off my parts, turn off my openings. They still exist, I just have graphically turned them off. In order to create the elements, which will essentially be tracing over this section, what I want to do here is to create some additional nodes that will guide me in generating those elements. So I'll use my tool option up here at the top to create a new node between 2 existing points. I'm going to turn on this option here to set the node type to standard. This allows me just to click 2 nodes. I click apply and we see the 3rd node generated. And I'm going to do this at various points throughout this cross section. Again, these are going to help me define my elements with the start and end node locations. We'll do so at this 3rd horizontal location as well as on the right side here. So clicking my first point, my second point, and finally we have a couple points down here at the lower left that we would also like to generate. So once we have completed the generation of the nodes, now notice I'm not creating these same nodes on the right-hand side. We'll be able to mirror our elements from the left to the right-hand side to save us a bit of time. I'm going to hold down my control key to select both of these center nodes and use my move copy tool. For this, I'm going to set the displacement direction here parallel to the y-axis. Then I can use my measure tool here by clicking on 2 points. I click OK, and you can see that those nodes are just simply moved to the center of this these vertical lines. I'll do the same thing for this node on the right by selecting it using my move copy, and I just simply delete the negative sign to move that to the center line on the right-hand side. So we'll begin by drawing our first element by right-clicking on the elements within the navigator to create a new element defined by a single line. Within this dialog box, we can take advantage here of the option to measure in order to set the thickness. So I can select 2 of these nodes to set the thickness automatically here. Then I define my start node, my end node. I click OK. I can hit apply and next, and notice in the background that first element was created. We'll do the same thing for our second element by taking advantage of the measure tool. I set my beginning node on the left and my end node on the right. I click apply and next. We have our second element created. We will set the measure option here for the longer horizontal element, and my start node will be on the left of the cross section, end node on the right. I click OK, apply and next. And finally, we have our last horizontal element, which I will use the measure tool once again at the bottom here from center point to center point. and my nodes will be on the left and on the right. So that takes care of all the horizontal elements, but I do need to create the vertical element on the left-hand side. We also have the ability simply to type in the thickness directly, 0.125 inches, and I select my bottom node here and my top node. I click OK, and we should see that vertical node, vertical element generated. So I will select the vertical element, hold down my control key to select the smaller two horizontal elements at the top, and I will take advantage of my mirror tool. So exactly like what we would see in AutoCAD, where I can create a copy to mirror about the z-axis, and I can graphically select my mirror point anywhere along the center line of this cross section. So when I click OK, we now see the elements mirrored to the right-hand side. So one final thing to do is we need to apply this tool up here to connect the lines and elements. And what I will do is to select the box over the entire cross section here. And notice when we do this, it's now broken this vertical element into segments. This is just purely so that the program detects where these horizontal elements will connect to the center line of the vertical elements. So now the generation of all of these elements is complete. We can click calculate, calculate all. We will now see the cross-section properties generated based on the thin-walled analysis. So a lot of these properties will be similar or very close to the finite element analysis, but perhaps if we take a look at torsion and warping, we might see some differentiation there. Because again, these are based on the elements, those particular properties, rather than that part that is created underneath what we're visually viewing here. So we would want to save this with the results somewhere on our computer so that we can bring in this cross section into RFEM. One other thing I just wanted to show you, maybe an interesting example here, is a custom extruded section that might look something similar to this. Now, this one was used with the finite element analysis. So this might be argument, hey, we're not so interested in local buckling for a section like this. It might act a little bit more like a massive section, not to mention just the complexity of trying to trace over these different elements. So you can easily apply the finite element analysis here and just not get local buckling checks, but still bring this section into RFEM to design according to the ADM per usual. Okay, so we will begin here in RFEM by taking a look at our base data. And the base data would come up when we generate a new model. You can see here the model name would be set, the type of model is set to 3D. Under our second tab, these are all the various add-ons that are optional that you would purchase with your RFEM license. And today we'll be working with the aluminum design. So you can see I have this turned on. I also have activated the wind simulation. So this will be taking advantage of our other standalone program, RWIND, for a CFD wind analysis for this type of structure. So we'll see that a little bit later on. Under the third tab, this is where we set the standards that we would like to use for design. You'll notice initially at the top, we want to generate our load cases and combinations according to the ASCE 7. You'll find here the NBC and many other international standards. The aluminum design here is set to the ADM. We also have the Eurocode available. For the ADM, we will be using the 2020 version. Under these settings and options, this is where we can orient our local and global axes. You can see that mine are set to upward. I also have turned on what we call the member representatives. And the member representatives, once we turn this on, will populate a couple different tabs up at the top. This is going to group together members that have similar materials, cross sections, lengths, so that we can better input data for the group of members rather than having to individually set this or modify this input information for each individual member. And we'll see how the member representatives can help us today. So once we have defined all of this data, we'll go back into the main program, and you can see for the sake of time, I have already modeled our carport aluminum structure here. I've also applied the loading that we'll go through. So let us take a look at the various cross sections and materials that we have defined. We'll begin here by taking a look at one of the columns. So I double click on this column. You can see the member type is set to beam. Under the second tab is where we can set the cross section. So when we define a cross section, we can visit our cross section library. And we have several thin-walled options here. So if your custom aluminum section fits into one of these categories, then you really don't need to use our section at all. But for anything outside of this, it might be advantage to make use of our section, that standalone program we were just in. But of course, we also have these standardized sections directly from the ADM. So for example, if we take a look at the hollow sections here, similar to the material library we saw in our section, we have our filters over on the left where we filter to the United States and to the ADM 2020, and we see our square tubes available directly from the standard as well as our rectangular tubes. We will also set the material within this same dialog box. So I have just set all members today to that same material we saw in our section, the 6061 for extrusions, but of course your materials may vary depending on which cross sections you're using. We can always access the material library here in the lower right-hand corner. It will look exactly similar to what we just saw in our section. We also have back under this main tab, the design properties. Notice this is turned on. This is relevant to that aluminum design add-on. This is telling the program that not only do I want to perform the analysis within the main program RFEM, but I want to take advantage of this add-on to also perform the design according to the ADM 2020. When I turn this off, notice multiple tabs up at the top disappear. We will only be using this member for the analysis then. I had also mentioned in the PowerPoint the transverse stiffeners. So this is a checkbox here that you can turn on, and we get an additional tab here where we can define a new transverse stiffener type, for example, some type of flat plate. And we can define along the length where these flat stiffener plates might be located. We can apply multiple plates. We define the material and the dimensions, and then again, that will be considered within Chapter G, the shear design of the member. So not so applicable for our example today, so we'll go ahead and leave this off. So looking at our cantilever beams, and I will double click on these to go over what we have going on. Same thing, member type is set to beam, but notice under this section tab, the distribution type is set to linear. We certainly have a deeper cross section where it connects to this column, and then we're going to linearly transition into the smaller section here at the cantilever end. So we do this by setting the distribution type here to linear, and then I would define two different cross sections at the member end and member start. So beginning with the member end here, if we take a look again at our cross section library, I have defined this as a T-shape. And we find T-shapes again by using our filter over on the left, and all the various sections are shown here. So I would go ahead and save this particular section. Now for the member start, what I also did is I created a new section and I selected again my T-shape here, but we have a nice feature down in the lower left corner where we can take any one of these standardized sections from the code and convert it into a parametric section. So all of the properties from that standardized section are brought into this dialog box, but I can make modifications such as the depth. Maybe I want to set this to 12 inches or 10 inches or whatever it may be. So once I have this defined, I would also save that cross section, and then you can see here I would define the two different sections at the member start and member end. Also under this particular member, or actually, well, you'll notice here that the design properties are also activated. So that's all that I wanted to cover for this particular member. Now, lastly, we have our custom extruded section, and this comes from our section directly. I'll kind of zoom in here and maybe turn this into a solid rendered view. We can see the true rendering of this cross section that was brought in from our section. And we do so, I'll go ahead and double click on this particular member. by selecting a new cross-section from our cross-section library, and over on the right-hand side, we can directly import one of those files. So make sure it has the saved results. We can bring in those cross-section properties, and like I said, even the rendering is there. What else you'll see here under the main tab is I have activated the eccentricities. So for each one of these purlin type members, I have created a member eccentricity here to offset it to the top of that tapered cantilever. And with these eccentricities, I have set the bottom of my R section member offset relative to member number 3, the top of member number 3. So the advantage here of using this option here for eccentricities relative to a section, this just means that when I make changes to the cross section, either my custom extruded section or member number 3, that eccentricity is automatically updated. If I choose one of these other options where I manually define the eccentricity, then if I make any changes, I have to go back in here and modify that eccentricity as well. So certainly a useful feature. Okay, so we also will take a look at these small purlin members here and notice that they are broken apart into 3 segments. And just with the complexity of the linear member, the eccentricity, in order for the program to detect here that these elements are connected, I had to break them apart. But we still want to design these members as one continuous member, and that's not a problem in the program. The reason why is because we have what we call member sets. So I can highlight the individual segments here in the center, hold down my control key to select the left cantilever, the right cantilever, and when I right click under the members option, I have the ability here to create a member set. Now the program is intelligent enough to determine which elements are continuous to create those individual member sets. So when I do, and I zoom in here, what we'll see then is a faint dotted line kind of grouping these 3 elements together. So now we can design the member sets instead of these individual member elements. We even see them listed out here in our navigator over on the left, each one of the member sets that the program automatically created. Okay, so that gives us a general overview of the various cross sections, the materials. Now I would like to get into the information that is relevant for the aluminum design specifically. And we'll begin with the effective lengths. Now I could go in here to begin with my column by defining the effective lengths, but remember when I was in the base data in RFEM, I turned on what we call the member representatives. The member representatives are now shown over here automatically in our navigator. It is grouped together similar members with cross sections, materials, lengths, and so on. So under the member representatives, we have our first group here for the columns. So when I double click on the member representative, we have the exact same tabs available to us that we do for the individual members. So when I go in and define an effective length, what's nice is that if I make any changes to the effective length, it will now be applied to both members 1 and 2, rather than having to individually go in and change each member. So let us begin with the effective length definition here. I'm going to create a new definition type, and you can see that this is all related to stability. So we have flexural buckling for the strong and the weak axis, torsional buckling, lateral torsional buckling. For lateral torsional buckling, we have 3 analysis options here. The eigenvalue method. So this is certainly a more theoretical approach where we will run an eigenvalue analysis underneath the hood to determine what the critical buckling moment is and use that for the capacity. The second option is user defined, and the third option is according to Chapter F. So if you want to directly relate to the ADM standard to calculate that critical buckling moment capacity, then we can do so here, and notice we get some additional information on the right. Now for this tube type section, I'm probably not so concerned with lateral torsional buckling or torsional buckling, so we can just turn those off altogether. For this second tab, I always like to make this first definition. I click OK and I go back in to edit it. The reason why is because now the program detects that this particular effective length definition should be applied to members 1 and 2, and this allows me to turn on a quick little view here directly in this dialog box of these two columns. So here is where we set the intermediate supports, and the intermediate supports will allow the program to automatically calculate the effective length, or K times L, to be used for the design capacity. And we're only looking at flexural buckling in the strong and weak axis direction. So for this column, we would probably want to assume that into the page here, out of the page in the local z-axis direction, it really should act more like a cantilever. But into the page, we have this additional column here on the right. Maybe this would be supported in that direction. So what we can do here is at the member end, go ahead and deactivate the support in the local z direction. So now that's acting more like a cantilever in the strong axes. Below, we will see the effective length factors, which default to 1.0. Now, if we're thinking to ourselves, I really have no interest in defining these individual nodal supports, I'd rather go in and just manually type in what K times L is. You can always do that by turning on the absolute values here. When we turn this on, kind of neglect these options up at the top because we're going to override them directly with the effective length KL in the strong and weak axis direction. Now for our example today, we certainly want to take advantage of these, so we will go ahead and leave the intermediate supports set here. So we can see our picture update for our particular columns. The local section reductions, we can create a new definition type here. This is exactly as it sounds, where we can actually reduce the cross-sectional area. And we would want to define at which X location along the member length we would like to reduce the area. We can put in the area of reduction here down in our table. And this is all related to Chapter D, Design for Tension within the ADM, as well as Chapter G, Design of Shear. So if we have any reductions, we could go ahead and input them in here. Now we don't for today's example, so we'll leave that empty. Now, the shear panel and rotational restraint are strictly related to the eigenvalue analysis for the critical buckling moment that I had mentioned for lateral torsional buckling. So probably quite often we won't be making any adjustments to either the shear panel or rotational restraint, so we can just go ahead and leave these empty. The design configuration gives us two options, the strength as well as the serviceability, and we have two default options set here. So let us go into the configurations themselves to talk a little bit more about what we're setting. So currently we have stability design turned on. We also have some limit values, and this just means that if our internal force falls below this limit that we've set here, we'll pretty much ignore it for the design checks. You can see the values are set quite low. Most importantly, though, is the local buckling. And the local buckling options that are given here are the three methods presented within the ADM. And primarily we're using this within Chapter E for compression design and Chapter F for flexure design. The weighted average method, the direct strength method, and the limiting element method. By default, this is set to the weighted average method, but you can go in and modify this here. The second tab, the stability, is related again to the eigenvalue analysis. It just tells us where we want to apply the loads. This is set at the shear point by default. For the serviceability configurations, quite straightforward here. We are just simply setting the limiting deflection ratios. So you can see the beam limit is set to L over 360, the cantilever is set to L over 180. Now for our carport structure today, this really isn't a building. We're probably not so concerned with deflection. So maybe we want to decrease this quite a bit to using something more like L over 120. And notice the cantilever automatically updates to L over 60. And you can create multiple serviceability configurations down here at the lower left if you want different members to have different serviceability limits. So we'll click OK there. Now, finally, we have the design supports and deflection. If I do absolutely nothing within this particular tab, the program is automatically going to assume that the member is supported at the start as well as at the end. But we know in this scenario here, we really want this member to act more as a cantilever here, kind of out of the page in the global X direction, but maybe it would be more supported at both ends when we're looking at the global Y direction or kind of into the page there. So we do this by setting what we call design supports. And I will create a new design support at the member start. So you can see here the type is set to general, and I'm going to support this only in the local z-axes. We do need to give it a support width, and this is pretty arbitrary. It's not going to be used for the design. We're purely just setting this width, and the support depth is automatically calculated by the width of the member, and it's going to be active for deflection design. Now, I'm not going to set this in the local y-axes. So we'll go ahead and leave that off. Now, when I click OK, what we see here is this element supported in the local z-axis direction. So it will be referred to more as a cantilever. So the L/60 limiting deflection ratio will be applied. Now, in the local y-axis, though, it is going to be considered supported at both ends. So that L/120 will be applied. So once we are done defining this input data for the aluminum design for our first member representatives, we also have the second set shown here within the same dialog box. And this is for my 4 cantilever tapered elements. So we'll begin with the design types here for effective lengths. We will want to create a new definition type. And for this, remember, I like to click OK and to go back in here to edit it just so that those members are now detected for this particular definition type. We will leave on the flexural buckling for strong and weak axis, as well as torsional buckling, lateral torsional buckling according to the eigenvalue method. Under the second tab, we will turn on our little view here in the lower right-hand corner. And by default, the program sets these restraints at the member start and the member end. And we know that's certainly not correct for this cantilever. So what we would like to do is for the program to detect these intermediate nodes where, remember, those purlins are framing into the top flange at the top of this tapered beam. So we can turn on intermediate nodes. Then what I'm going to do is to use this option here to select the member graphically. So I'm kind of put back into RFEM here. I select any one of those 4 members, and notice now I have additional rows here within my table because it's detected those nodes along the member length. So right here at the member start, you can see that the program has restrained this in translation in the local Z and local Y direction, as well as rotation about its own axes, its own x-axis here. So we'll go ahead and leave that as it's set. For the second node, we want to restrain only in the weak axis direction. And remember, this purlin is framing into the top flange. So we can also set an eccentricity here to the upper flange. The next node, same exact concept, the weak axis, but we add in this eccentricity to the upper flange. The third node, same concept here as well. We add in the eccentricity to the upper flange. Now finally, our fourth node. By default, the program has restrained these degrees of freedom. Of course, we know this is not the case, so we will simply turn those off. And lastly, to apply that same eccentricity here to the upper flange. So now when we click OK, what we see are those intermediate supports automatically applied here to the top of that tapered element. Jumping to the design supports, what we have here is certainly a cantilever, I would argue, in both the strong and the weak axis direction. Nothing is supporting it at the right end here. So again, if we do nothing here, the program assumes that this element is supported at the start and at the end, which is not the case. So what we will do here is to create a new design support. And the reason why I'm creating a new design support is I'm going to take the same approach that we saw for our columns by defining a support width here of 6 inches in the z-axis, but I also want to turn it on here in the local y-axis. And we'll go ahead and adjust this to 6 inches. So now when I have applied this second support to the member, the program will automatically detect that it is a cantilever in both of those orientations. Okay, so now that we have set up the input data for these two member representatives, we also have the individual purlins here that, remember, we created the member set. So this member set is going to have its own member set representatives located a little bit further down here within our navigator. So we'll go ahead and double click on this to really apply the same workflow. It's just simply in a separate location because it's considered a member set rather than a member. Under the design types, the effective lengths will create this new definition type. And again, I'll click OK here and I'll kind of go back in to edit this one. I want to turn off torsional buckling, lateral torsional buckling. Maybe this is a little bit more of a tube type section, so I'm not concerned with this. And we'll jump to the nodal supports and effective lengths. Now, again, by default, the program sets these nodal supports here at the member end, which is not correct. This is really a cantilever type scenario here. So we turn on the intermediate nodes, and I once again graphically select, not the member this time, but I'll select that dotted line kind of that's grouping these three segments together so that the program will generate a couple more rows here to detect those intermediate nodes. And at the member ends, I'm just going to go ahead and turn these off because remember, we kind of have a cantilever type situation. But rather, where it frames into the tapered cantilever sitting below it, we'll go ahead and restrain this element here in both the strong and the weak axis directions. So now we click OK, and what we should see then are intermediate restraints update here to the interior nodes instead. Now the design supports is interesting for this member as well because again, we have cantilever out here on the left and right, but we really have a supported type situation between the interior nodes. So once again, even for this complex situation, we can take advantage of the design support definition, but this time for the internal nodes. So what I'll do is I'll use my drop-down box here to create a new design support for the last time. This time I'm going to give it a design support width of 4 inches. That's just the width of that T section sitting underneath it. I'll go ahead and only activate this in the Z-axis direction. I'll click OK, and now we see that design support activated here. I'll just simply use that same definition type for my other internal node, and now we see the design support on the right-hand side. So this will now be using the L/120 for this segment here in between the two supports, and then on either end, it will use the L/60. So now I have defined the effective lengths. I've also defined those design supports. What's nice is that in our navigator and specifically under the display options, we can actually see that information that we just set shown graphically. So for example, we have here types for members where I can turn on the design supports. Maybe I'll turn this to wireframe view. So if we're interested to see those design supports that will be used for the deflection check shown graphically, we can show them here. In a similar manner, we have the types for aluminum design, and we can actually turn on those intermediate nodal supports that are being used for the effective length definition if we'd like to see those graphically. Now, by no means are we applying these as supports for the static analysis. This is purely used for the design to determine the effective lengths automatically. So we'll go ahead and turn those off as well, but I just wanted to point that out. All right, so we now want to take a look at the loading of the structure. And for the sake of time, once again, I had mentioned that I've already loaded this structure, and you'll notice I placed a surface on here at the left and right side. And the surface is a bit special because if I double click on it, it has this stiffness type set to load transfer. And this is new within RFEM 6. It's not adding any stiffness to the structure. Notice the thickness and the material are grayed out. It's purely used to distribute loads to the members. And under the second tab here, we have load transfer. We can set this to one-way area load distribution based on the local X or Y axes, or two-way area load distribution based on both axes. I have this set to the Y axis. So what this allows me to do now when I take a look at my applied dead load, which is just a simple surface load, I can display the load transfer separately here within my navigator display option. So automatically the program will distribute the loads to each one of these purlin elements based on its tributary area. And we have two loads applied here at the center element because of course we have a surface on the left and a surface on the right, so it should see a load from both sides. Now we can turn this off to go back to the display of the surface load here. Same exact concept for the live load. I just decreased the magnitude slightly to 5 pounds per square foot. Now, if we take a look at our load cases and combinations, here again is the dead load and live load applied. I also created a third load case here. So pretty simple application for today's example. But this wind load is a bit different than the standard static loads here for dead and live load. And the reason why, if you remember, back under the base data, I activated wind simulation. So this is going to integrate with our standalone program, RWIND, for a computational fluid dynamic analysis, or CFD. It will take the structure out of RFEM, place it in this numerical wind tunnel, and we'll go ahead and see what the wind pressures are. So why would we want to use this? Well, when we refer to the ASCE 7 for freestanding carports or freestanding canopies, there really is no guidance in the code on minimum wind loads. We're simply supposed to treat this structure like an open building. So this could be a disadvantage in some scenarios because the minimum wind loads are much too high, or maybe they're much too low. So it might be worthwhile using RWIND, the standalone program, as just an additional tool to compare to the minimum wind loads that are set forth within the ASCE 7. Notice here for this load case, the analysis type is not set to static analysis, but now it's set to wind simulation. And under the second tab, this is where we can control the settings. We can also set the wind profile. You'll notice I have this set according to the ASCE 7. So my wind velocity as a function of my structure height is shown over here on the right-hand side. Now, of course, we could get much more into this, but we certainly don't have enough time for today. But we do have webinars on our website dedicated entirely to RWIND. What I can do, though, is to take a look at here using this button to calculate the RWIND model. And it will go ahead and launch RWIND as the standalone program. And what you'll see here is that my structure was brought in to this numerical wind tunnel. If we zoom in here, even our custom cross sections from our section are brought in. You'll see the tapered elements and of course the surface element shown here. And our numerical wind tunnel is shown or indicated by this box, and we have the wind flow kind of coming in from left to right here. Now I've already solved for this model, so what you'll see eventually when the calculation is complete is the wind pressures on this carport. We can kind of move our mouse around to view what the wind pressures are both on our column elements. We can kind of turn this upside down here to view on the underside of the carport and just what the various pressures will be based on this particular analysis. We also can view the pressures in and around the structure. So we'll use our slider tool here where you can kind of move this back and forth to view the different pressures. Same concept for velocity. So we really see how the wind speeds up underneath the carport as well as up here at the upper left. And finally, we have what we call the velocity vectors. So we can see, indicated by these colored arrows here, kind of the magnitude and the direction the wind load is going to move around the structure, also turning on our streamlines. And everyone's favorite, these streamlines, we can also display as a flow animation. So we can see the particles kind of hitting this structure, moving on and around it. But ultimately, what we're trying to get out of this calculation is back to the wind pressures here. So once we're done with the calculation in our wind, and we can do all this underneath the hood without even opening our wind at all, what you'll find within RFEM is we'll bring these loads back into the program, and we can combine with dead load and live load and so on. So under the Design Situations tab, there are two design situations that are generated here, LRFD and ASD, and this is automatically done based on the ASCE 7 standard. So LRFD is going to be our factor load combinations, and ASD is going to be our unfactored load combinations. And you can see that these are active here for our aluminum design add-on. Design situations are used within the design add-ons, and we can create multiple design situations. You can see down here in the lower left corner. But ultimately, looking at the load combinations, we can see the individual load combinations that are associated with each one of those design situations. So we have here first design situation number 1, LRFD, or our factor load combinations, shown here in orange. And we also have our second design situation, our unfactored load combinations that are associated with design situation number 2, shown in red. So once we have defined our load cases, our load combinations, we've applied the loads to the structure, we can take a look at those individual load combinations here in RFEM. We can view the loads applied to the structure. Here's our numerical wind tunnel directly from our wind. Here's the dead load, live load, and so on. So we're almost ready to run our calculation, but remember the huge advantage of RFEM 6 is the integration of these add-ons, such as the aluminum design add-on, within the main program. So no longer do we have to run a static analysis and then run a separate design calculation. We can do everything together. So before we do, we need to address a couple other settings. So we'll take a look at our table, and we're going to drop down to the aluminum design add-on. This is available because I activated it way back when under the base data. And our first tab here shows those two design situations, LRFD and ASD. So we need to take the design situations and relate them to the limit state type. So my LRFD I currently have set according to this dropdown to the strength limit state design LRFD. My second design situation I have set to ASD, where I have set this to the serviceability limit state design. So I'm going to take those unfactored load combinations and use them to check deflections. Now, if you are doing ASD design, maybe you would want to create a second copy of your design situation ASD. We could completely deactivate LRFD, and instead, your first design situation here for ASD could be set to strength limit state for ASD. Your second one could be set to serviceability. So we'll be utilizing the LRFD here for today's example. Now, the second tab is the objects to design. By default, everything is turned on. So what I want to do here is to turn off the design of my member representatives. I will design all member sets. If you remember, that's that custom extruded section here that we group together as continuous members. For my member design, what I would like to do is to graphically select, I'll kind of clear out these options here, my two columns, and I will select, not that one, my 4 cantilevers here. So we should see all of those members populated. I click OK, and I see one small error here. Member number 41. Let's see which one that one is related to. So the 2 columns here, and then we will have member 1 through 3, 33, and then one final element here. Okay, that should be good. All right, so we're only designing those members, which would be the 4 cantilevers as well as the 2 columns, and then again, those member sets. So now we're finally ready to run the calculation. We can either run the calculation here in our toolbar, or we can go up here to calculate all, and this actually will solve quite quickly. We're running through our load combinations, uses a multi-core processor on your computer, much quicker in RFEM 6. It runs a design according to the ADM, and we're now presented with our results. So let us begin here with the static analysis. We now get a new tab within our navigator, and over on the left, we have the static analysis option available in our dropdown. So we can view the global deformations, and we can kind of scroll through these different load combinations at the top just to see exactly how the structure is behaving under the applied loads, see if it's as we would expect. Now, of course, we're also very interested in the member internal forces. So we can turn on, for example, the normal forces. We see pretty high normal forces for our columns, as we'd expect. We can take a look at shear forces in the weak axis direction, the strong axis direction, maybe bending moments, and also, as we expect, where these cantilevers frame into the columns, we have pretty high bending moments. So for any one of these members as well for the static analysis, we can always right click, and under the member options, we have the results diagram. And the result diagram is just simply going to give us a little bit more information where we can turn on internal forces, deflections, whatever it may be, and show it more detail along the member length. We can even scroll through to the different load combinations directly within this dialog box, add this information to our printout report. And new within RFEM 6 is that you can drag this over to your second monitor, and you'll be able to work concurrently in RFEM in the background. So the static analysis, fairly straightforward, just viewing the information purely from the applied loads. We also have the same static analysis information shown in table format here, so you can view the results by member. Notice everything is kind of synced up in the background here to show me exactly where that controlling internal force is that I'm looking at in the table. It will point that out with that red arrow on that particular member. We can export this to Microsoft Excel for further sorting options. So everything is possible here. Now I'd like to jump down to the aluminum design. And here we can take a look at our results by design ratios on members. And we'll take a look at the design ratios by member tab. And notice once again, the program is syncing up to the table here, so I can kind of take a look at each one of these design checks. Now for each one of these members, we are giving you every design ratio from every chapter. So we'll see here multiple design ratios from chapter E, F, G, H, and even L for serviceability. If you're thinking, it's really too much information, I'm only concerned with the max design ratio, we can always use our filter in the toolbar here to filter to the max. And now we're only going to see the design ratios that are applicable. A lot of these are controlled by deflection, for example. But going back to no filter, I thought it might be interesting here if we take a look at the design ratios by the section. And we go into our custom extruded section that we brought in from our section. And sure enough, here for one of the checks is local buckling according to chapter F. Well, new within RFEM 6 as well is this design check details. So this is going to give us the code equations that, again, we can follow line by line. The variables are listed here. The code references also on the left-hand side, just to understand, again, where the ultimate design ratio is coming from, rather than kind of being a black box software. We can follow, again, line by line. But again, because we ran this custom extruded section according to a thin-walled analysis and kind of took the time to trace over that element, we're now going to get section classification here for local buckling. And if we take a look at element number 5, for example, we can see here exactly how that element was classified according to chapter B, and the local buckling checks will now be carried out according to chapter E and chapter F. We also can take a look at this option up here in the upper left, the diagram and section. So this is nice that we can use our dropdown to view the stresses on this custom section. So currently we're looking at the normal stresses, primarily in tension, but we can use our dropdown box to view any one of these stress options available here, including shear stresses as well. So also within the same design check details, we can also access our result diagram. We already touched base on this, same thing that we saw from the static analysis, but if we'd like to quickly access the internal forces that are being used for design, we can do so here. You also can get the various checks from the same X location. So if we jump to one of these other checks from chapter F for yielding, again, we're going to see every single equation listed out here and able to follow it one by one. So we'll go ahead and close out of this. Now everything is visible in this table format, of course, but we also have some graphical options. Currently we're viewing the design checks, the ratio envelope. So essentially just the max of all design checks is currently what we're looking at on the structure. And we can compare this to our color panel over here on the right. What I thought would be interesting to show is if I take a look at this tapered cantilever beam, and we'll create a visibility by the selected objects. I'm going to turn off the design check, and remember the rendered view looks something like this. But underneath the hood, everything is created as just a center line here. What we can do is to take a look at this particular member for lateral torsional buckling. And when I click on that option within the table, we're currently viewing the mode shape. So I took that eigenvalue analysis method for the LTB checks. And underneath the hood, this eigenvalue analysis is run to determine what the critical buckling mode looks like for this member before it fails. And this is what we use for the capacity calculations for LTB. We can also take a look at here to decrease the factor a little bit, just to see in a bit more detail what's going on with this tapered element. So kind of interesting there as well. Okay, so hopefully that gives you a better summary of just how we can create those custom extruded sections in our section, bring them into RFEM, and to really run the full analysis and design for our aluminum structures. So I'll go ahead and jump back to the PowerPoint to close out our presentation today. So I always know this is quite a bit of information packed into 1 hour, but we record these presentations and they're available usually within a day on both our YouTube channel as well as the web page that you use to register for this webinar. You can even download the RFEM model that I used today as well as the RSECTION model. You can open it up in the 90-day trial version that we offer. So that is full capability RFEM. It includes all add-ons for the full 90 days, same concept for our section. If you have any questions about today's presentation or any of our products, feel free to contact us at our Philadelphia office with the information shown here at the bottom. That's 267-702-2815 by phone or by email. You can reach us at info-us@deluwell.com. So we will have many more upcoming webinars. You can register at deluwell.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so feel free to sign up directly through the email as well. PDH certificates will be automatically emailed to all participants who were here for the full presentation. So the full 60 minutes, this is a requirement by the states that we are pre-approved providers that if we issue the PDH, you must be here for the full presentation. Now this isn't done immediately after the webinar ends. It will usually be sent out within a day or two. So just have a little patience with that it won't come immediately after this presentation ends. If you watched with a colleague or you watched in a conference type setting, you can go ahead and request PDH at info-us@deluwell.com. So again, if you yourself did not register with your own name, your own email, just go ahead and send us an email here. Let us know who you watched it with, and of course, ensure that you were here for the full presentation, and we'll be happy to issue PDH as well. And with that said, I want to thank everyone for attending, and as always, we hope to see you at the next webinar. Thanks.